Jason and I are going to talk to you a little bit about an interesting project that we got involved with that happened about, well, actually 6 months to the day after the Brent Spence Bridge fire happened. So we were called upon for this little event, and we got a short video here to play for you to kind of introduce the project. So we'll go ahead and get that kicked off and get us underway.
I am here a brief section here on the I-40 Mississippi River Bridge. We just found a super critical finding that needs to be shut down.
TDOT says that RDOT inspectors found a crack at a support beam. River traffic barges are also shut down until further notice.
The situation with this bridge may be a regional issue, but it is a national concern.
Those in Memphis, those outside Memphis, even to the White House, everybody understands how important these bridges are in this particular corridor.
The significance of the Hernando to Soto Bridge across the Mississippi River is hard to measure. It is a vital link between the east and west of the country. It connects Dallas to Memphis and beyond. And the amount of freight tonnage that goes across that bridge every day is huge.
I think the initial reaction was disbelief. It was one of those things that is so severe we didn't see it. It's truly hard to believe something that that's possible and can happen. To actually see it in real life is startling, but it definitely took a few minutes for it to sink in.
Because we had only seen the crack from the top, we really needed to understand the extent of the damage around that member. So the UAS team set up on the bank of the river.
The design of the repair of the Hernando to Soto Bridge was challenging because one of the first things that we had to do was really to determine whether or not it was safe for the work to be done on the bridge. We had to understand what the condition of the bridge was, at the point of the fracture, how much load was in the members, and how much stress was going in other places of the bridge. So we focused on getting the bridge stable so that we could strengthen it first and then safely work on the bridge and reopen the bridge's traffic.
From a client's perspective, TDOT's looking for a solution that will carry this bridge for decades and decades to come. The design team is looking for a repairer that they can stand behind, that they know will meet TDOT's goals. And from a contractor's perspective, we're looking for, first and foremost, in this case, emergency repair job. How can we implement a repair as quickly as possible and get traffic open, but also maintain the safety of the personnel doing the work and no further damage to the bridge itself. Basically, put the bridge back to where it would have been originally, plus added additional capacity, which ultimately does give TDOT and RDOT confidence to tell the public that this bridge will be here. It will be here as a landmark in Memphis for decades or 100 years to come.
Everybody's focused and advocacy to get that bridge open, to do whatever was needed, working together was pretty incredible to me. And there were so many people involved at one point or another, and each one had a very important part of getting that bridge open.
The multi-agency coordination was amazing. It was RDOT, TDOT, the Arkansas and Tennessee Federal Highway Administration offices. It included also that we brought in our consultant, AGCD, Michael Baker, and the contractor TDOT, who came on board pretty quickly after the fracture was discovered.
So I can imagine what the people of Memphis and the people traveling through Memphis were feeling at the time. So I appreciate whatever patience they had. I appreciate thankful for their patience. And I appreciate all the people that were involved in this process of getting the bridge open safely and quickly. Thank y'all very much for what you did to make that happen. Thank you.
All right, so that gives you a little bit of an introduction to the problem and the scope of what we were dealing with on this situation. It also really relays the importance of this crossing to Memphis and to the regional population down there. So we're going to talk a little bit today about the immediate response, some of the modeling and analysis that was done, our three-phased approach to getting the structure reopened quickly, and some of the lessons learned along the way. So the Hernando to Soto Bridge is located between Memphis, Tennessee, and West Memphis, Arkansas. It's named for 16th century explorer Hernando de Soto. And he reportedly died over the south Memphis after exploring the stretch of the river there. But, you know, you'll recognize the bridge. It looks very similar to one that we've got just here on the side of West Louisville. It's not unlike the Shirley Minton Bridge. There's a lot of parallels there. We'll talk a little bit about this. This is a two-span continuous tied arch bridge. It's 900-foot spans, and it was designed by Hazlett and Hernando. The other things to note about this is obviously it's a very important connector to the regional community here. And it opened in 1973 for the cost of about $57 million. And locally in Memphis, it carries 6 of the 10 lanes across the river. Now, the importance of the bridge is really underscored back in 2000 when the two states combined and started to realize that they needed to retrofit this bridge for seismic considerations. That caused about a $200 million investment to improve the resilience of the structure for the long term here. So very important crossing for the local community. So, you know, obviously we've got an emergency out there. There was a critical find. So we set our heads together to try to figure out what we could do first and how we could do it quickly. We drew upon a lot of lessons learned. As you can see, we've got an emergency response plan that we developed after the Brent Spence Bridge. So we started beginning to go through that and gathering as much data as we could, and then putting together teams of engineers so that we could solve this problem quickly and efficiently. You'll see here, in addition to the field response, we had a number of different teams that we had to get involved. So we immediately began to assess the problem, diagnose it, and try to compartmentalize it into different areas that we could work on. We knew we had a team that ultimately had to strengthen this bridge so that we could work on it. We knew we needed the analysis to get going immediately. And we also saw some individual solutions such as post-tensioning as having some benefits. So we began to quickly mobilize our teams to really get productive and get to dive in on this project. This was something that we knew it was not going to be a 9-to-5 kind of challenge. This was one of those things where everybody's got to be committed to the project. We pulled a number of different doers in from different projects in different parts of the country. All told, we had about 60 individuals working on this project from 20 different offices across our company. So not knowing the full severity of the fracture, we set about to use our UAS technology and techniques. You can see here, they set up on the banks of the river on the Memphis side and really started to monitor that. Now that bridge was being monitored after the fracture by both RDOT and Michael Baker. Both companies, both organizations used drones to monitor and scan the rest of the bridge because we didn't know if we were dealing with a one-off crack or if we'd be finding other locations out there. We needed to know the severity. We needed to know if there was any distress elsewhere in the structure. So a complete scan of the bridge was really a helpful thing to give us some more information on that. So again, they set up on the side of the river, and one of the things that we did was really a kind of a unique thing. We wanted to get more information on this fracture. This was a couple of days into the project where we had identified a potential repair option. But in order to move forward with that, we really needed to know how much that tie girder had displaced during the fracture. So we set up to use kind of a combined UAS and rope access mission, if you will, to get out there and get some hands-on details. So what you see on the left-hand picture there, the woman's got a monitor there where she can monitor what the drone is seeing through there. So we utilized the drone to capture the rope access and used it also for communications. One of the things that we did during that was we utilized a conference call, Teams meeting, if you will, so that we could communicate effectively with the inspector in the field by Bluetooth. He had his cell phone and his earpiece and was able to hear what we were looking for. And that video goes something like this. And the voice that you'll hear here is Jason talking and narrating to our inspectors.
Relative awareness of the top of that plate down through there. So we're eventually going to be bolting plates on the side. Can we get a sense of how far down the tie before it gets back to being relatively square and schematic? Does that make sense, Jeff?
Yeah. All right, right there at the end of the display plate for my right arm here. I've got 0.2%. Top being away from the bridge.
So for the sake of time, I'll go ahead and move on. What that really did for us was that gave us real-time information, right? This was a real good opportunity for us to get data directly from the field. There was no confusion over what was being measured or how it was being measured, and any additional measurements that were needed were gathered immediately. That was an extremely powerful thing for us because we had real-time data that we could work with. We were able to take that back and modify designs and make sure that we had clearances that we needed to make connections fit up. And you can see some of the photographs that were taken both from the drone and also from our inspector of that fracture location. You know, again, these were some of the early indications that would eventually tell us a lot more about what happened with that fracture. And then the lower right hand, just to orient you, that is actually looking at the bottom side of the box, looking up at the end of the fracture. So this fracture occurred in span B. Again, this is a 2-span continuous bridge. It's completely symmetrical about the center pier. You'll notice that the fracture location occurred a couple of panels away from that center pier. So on the north side, the upstream side of the bridge, but you can see the basic floor beam and geometry of the bridge there. Now, to really understand the problem that we were dealing with, you've got to kind of understand the detailing that was involved with this. And this bridge was set up, like I said, almost exactly like Sherman, you know, almost. The floor beams were spaced at about 75 feet on this, or I'm sorry, the floor beams were spaced at 37.5 feet on this, and individual field segments of the tie girder went about 75 feet. So they essentially went from even joint to even joint along the bridge, and then they were connected at those field splice locations. Now, they were dealing with really thin material out there. They were utilizing 100 KSI material to lighten that tie girder and make it very efficient. But the problem that led to was at these bolted connections, at any connection, really, they had problems with net section fracture on this girder. So they had to upsize or upset those plates to 2 1/4 inches in order to make the connections work. Okay. So what that left us with is, you see those 4 rectangular boxes down there. Those are all individual welds, full penetration, full joint penetration welds that went at each one of these tie girder locations in each segment. So you had 4 welds times 4 on the top, 4 on the bottom, 4 different faces of that. So you had a number of welds that were stacking up here really quickly. Now, the one major difference between this bridge and Sherman Minton is accessible on the interior. There's actually holes that you can get in, you can go in and you can inspect these welds. They have the same type of welding issues, but you can inspect them from the interior. This box was completely sealed by diaphragms just at the end of those bolted connections. So these welds were inaccessible for really the life of the bridge. Nobody was able to look at them from the inside, only from the outside. So that's an important detail when you start to look at the welding connection. So this is a picture of the inside of the box. You can see here the weld. You can see the 2 1/4 inch plate on the left and the 1 3/8 inch plate on the right. Again, major transition thickness there. You've got the bevel, and then obviously the weld material that's deposited there. It's real easy to find these welds on the inside of the box if you can get access. Not so easy on the outside where everything's ground smooth and you've got to locate them and everything else. So being able to make sure that you're looking at the right area is a critically important thing. So obviously we know at this point that we've got a fracture, but we need to understand fully how bad it is, right? We knew we had 100 KSI steel and the base design gave us about 38 KSI in just P over A. When we take that fracture out, we lost 55% of the overall section of the tie girder. It's a tremendous amount to lose. But thank goodness they were working back in allowable stress. So they had some pretty significant margins back then. When you take that material out, you're left with about a P over A of 83 KSI. Okay, you're still under yield, right? Well, there's a few other things that we haven't accounted for yet. Eccentric loadings, right? We've got a section that's no longer a box. It's now basically an angle being loaded through the center of the box. So we took that and we took to a refined analysis. This was something that actually Jason did overnight. That first night was kind of create a crude model that we built off of to give us better and better results as we went along the way. That refined analysis showed that we had some significant issues there. We had some very high stresses. We were over yield in some locations on that box. And there were a lot of unknowns that we really didn't know, right? We had the planned dead loads, but we didn't know what the structure actually felt or actually experienced. We didn't know how much load had redistributed throughout the structure. Again, transient loads and other factors that came into play. All in all, we were dealing with some very thin margins of safety out there. And that's why we were very careful about the approach that was chosen and taken there. So again, just to talk a little bit more about the modeling and modeling philosophy, we built upon the simplest models. We started with a 2D model, matched plan geometry, matched plan loads to give ourselves confidence, built a 3D model, and then expanded that out so that we would refine that loading, refine those models all throughout the way to, again, build that confidence and make sure that we understood the behavior One of the important things for us was always to identify, were there other alternate load paths that we could account for? In a structure like this, in the tie girder, there is not. It really isn't got another place to go because it's going to overstress the bearings and the other framing members. So we began to look for solutions. How do you fix this thing? We explored a number of things from the permanent fix to a number of different temporary solutions. And one of the things that really started to show promise was to lengthen a splice and basically go from that field segment to as far as we could get on the other side. So that was the direction that we kind of set forward with and we were looking into. We worked very quickly with Stith and a lot of local fabricators to identify materials. Stith happened to have some material on hand in HPS 70 in stock that was suitable for the repair effort in this case. And it was important for us to be able to design a repair that we could actually get the material quickly and efficiently, because otherwise we're going to be waiting for materials and it's just going to increase that schedule. So one of the things that TDOT identified early on was the need to go to CMGC on this project. They understood the complexity, they understood the risk, they understood the importance of means and methods for this particular project. So with that in mind, they set about to advertise on Friday, May 14th. And our goal was to have plans delivered, and we did. We had that out there ready to go 3 days after the incident happened. So they left that out to the contractors on Friday, asked for their responses by Monday. How are you going to approach this bridge and fix this bridge? So by Monday, they made the selection of the CMGC contractor based on qualifications, their related experience, their availability, and their particular approach to the repair options. So that Monday, they selected Kiewit Infrastructure to do the work. Now, it's an important thing to think about. Why would you use CMGC on a project like this, right? Well, it's really about risk control. You use CMGC whenever innovation is needed, whenever you're trying to mitigate risk, or potentially whenever you've got some need for collaboration. The means and methods really help to drive that. We needed to collaborate on how this bridge was going to be repaired because we knew we had some potential issues out there with the high stresses that we were seeing. So once Kiewit was on board, they immediately started collaborating with us. And that was really a key to the success of this, to drive down the risk. One of the things that we were concerned about from day one was really getting out there and starting to hammer on those bolts with an impact gun, right? You're sitting there with a fracture less than 18 inches away from you as you're sitting there with an impact gun. We didn't know what that was going to do to the structure. Nobody knew. We knew we had to be careful at this point. So as talking through that, obviously we wanted to come up with the best solution possible. We began to gravitate around these solutions of extending the overall length of the repair. So what you can see there is an extensive repair in the bottom right-hand corner from the BIM model that we developed. And you can see that it extends into the next panel point, into the next section of tie girder. That was an important decision for us in terms of driving down the risk, but it was also an important decision because it would drive the direction of the project and increase the scope of the effort for the phase 2 repairs, as you'll see later on. Now, again, we took that design change, and we processed it immediately. We had crews working overnight to get those plans done. And by the next morning, we had plans ready for TDOT to bless and send off to fabrication. So they released them for fabrication the next day. Stith and their crew got involved and started doing the shop drawings immediately. Within 2 days, had shop drawings. Fabrication began on the 21st. And by the 22nd, day 11, TDOT had steel loaded up on a truck and bound for Memphis. So with that, Kiewit wasn't exactly sitting on their hands. They were hitting the ground running. They immediately started setting up a work platform underneath the structure. And you can see from the picture in the upper right-hand corner, once that steel was delivered on site, they were ready with these come-alongs to get out there, get that steel into position and fly it over the site so they could start bolting things up. So it was really a very efficient process. With their chain falls out there and everything else, they were able to get that steel in position. The phase 1 plating was installed and completed on Tuesday, May 25th, 2 weeks after the fracture had been found. And what that allowed us to do then was to really start the rest of the repair work. We were working on the phase 2 repairs all along the while in the background with a separate crew, but we were able to then get started on the next phase and subsequent phases and turn our attention to that to more fully focus on that. So phase 3 was really about inspecting this bridge, giving it a clean bill of health to reopening. You heard in the video about reassuring the public, and that was one of the things that RDOT and TDOT wanted to do in the midst of this, was to make certain that there were no other issues out there and that this bridge got a clean bill of health. So Jason will talk a little bit more about the inspection effort in the end and the forensics there. So Jason, you want to come up?
Thank you, Aaron. As Aaron mentioned, the first step of this was just to stabilize the bridge. We had to ensure the safety of our structure because of the fact that we had very little confidence or had so many unknowns that we had going along through there. And so at this point, we had to say, all right, how can we get this from being stable to a permanent fix? We got to be able to allow the public, everybody to be able to drive on this bridge. And that was the next stage. So as you can see here, this stuff is, back it says 511. This is day one again of a team working. How can we fix this permanently? So we have the displacement, we've got movement of the tie. We had to get some of the load back out of it. So almost immediately came to the idea, we're gonna have to post tension this thing, squeeze the tie back together and try to find a way to figure out how to do this. And so that was our concept. We're gonna post tension this thing and work through it. So let's talk a little bit about that thought process. As Aaron mentioned, in a presentation like this, we're going to get up here and tell you the story, and it seems very linear. But for the people that have been through something like this, it's never that way, right? You run down a lot of blind alleys, you run into a lot of dead ends, and you've got to run down a lot of loose ends that just fail. And that's just part of the process, right? But you have to work your way through this and to find the best solution. And that's essentially what we had here as well. So when we came through here, our initial thought in the direction from the owner was we've got to get this tie out of here. We've got to get it found a way to remove this tie. And so this was our concept. We're gonna come here and post tension this bridge up, remove the tie and replace it with a new steel tie. And as Aaron mentioned, we developed this BIM model that was allowing us for visualization and flash detection and things. And we showed this to the contractor and they said, you want to do what? And it was really this picture that really kind of, I don't say scared people, but it kind of eye-opening, right? Communication is really important. And anytime we're doing, really, that's our job as engineers, to communicate an idea to a contractor. And it was this communication, this visual communication that really hit it home. They said, you want us to have this bridge held on by thread. And now these are 3-inch steel rods, so it's not exactly thread, but that's the idea. And that was a picture. They said, well, what if we have a crane that drops part of that new tie and hits one of these things? What's the redundancy? How are we going to look at this thing? And it gets back to that communication, means and methods, talking to the contractor. So they said, well, we would like to try something different. In the end, we did, right? We ended up not cutting out the tie, but we ended up doing a similar approach to what we did out here on Charlotte. We did post tension it, but then we came through afterwards and put in plating along each side of it that would be able to take the full load if the tie were to continue to fracture. There was another issue with the tie at that point. So let's talk a little bit about it. What do we do on the post tensioning? The post tensioning thing for this were 8 3-inch diameter rods. We had very large weldments. That's what you kind of see, in the color graphics there with the analysis done on these large weldments. We had to be able to take the load from those post tension rods and bring it back into the bridge and vice versa. So following that load path all the way through there, all the different twists and moments and things. We did allow for a certain amount of these imbalance as would happen while we're stressing these things and having to be able to understand those interactions. Again, we have the model here. We use it for flash detection. There's a lot of details on these old bridges that you have to try to miss, where they're stiffeners, where we have to add some extra plating in here, etc. All these things are very useful for that. Graphically, what do we do to try to understand this for those that are trying to understand what they were playing around this? And any one of these things, the outside isn't quote unquote smooth. We're going to have other splice plates, other things in the way. So what you have to do in a project like this, we came in here and took out the fractured region. Then we're going to come in here with some of the actual main plates that run the length of the tie. Well, we have a splice here we've got to work around. So we actually have to come in here with some cheese plates and some additional splice plates that run around our tie, and the same thing on the inside and the out. So we have to kind of piecemeal this thing to try to work around what's in the way, all the different portions of it, and make that happen. In the end, here's a couple of pictures of what that looks like in person. These are fairly large weldments that get put into place here, right? You got a lot of bolting and things that we're going to do here. We're connecting these into existing splices that were out there. We were able to exchange these bolts out and make this all happen. For those that haven't seen a post-tensioning operation, the way we did this, we were able to have 4 post-tensioning jacks. There were 8 rods, but we did these symmetric. We had 4 of them doing symmetrically insides and outs of this thing to try to make sure that the post-tensioning didn't add some eccentricity and additional damage, right? It's kind of the do no harm approach that was mentioned in our video that we continued to work through the entire time. We had to do quite an extensive monitoring program. We had a lot of strain gauges. There's a Dynaforce, which is actually a part of the post-tensioning that can tell the amount of load in the post-tensioning rods themselves. And so we were continuously monitoring the bridge to see, was it behaving the way we anticipated? Were we getting the load out of this thing? How much of the post-tensioning load that we were applying at each end was coming out of the tie? How much of it was going into the secondary member? All these sorts of things. The other parts of it leaks through floor beams and into other aspects of the bridge. That's kind of an inefficiency. So we had to understand the efficiency of the post-tensioning to make sure that that load was getting in there and that we were removing a sufficient amount of it. In the end, we took out somewhere in the order of about 1.5 million pounds, about 1,500 kips, I think is what came out of the tie girder, out of, in the order of about 4 million pounds of what was in it, design dead load. When we get to this point, we finally, I guess to me, I felt a lot safer, right? We had this phase 1 approach in, we had the post-tensioning on this thing, we reduced the overall stress in the cross section, feel a little bit better. We did remove the fracture so that we can do the forensics on it. I'll talk about that just here in a minute, why we think this happened or how this happened, etc. But we were able to remove that. In the end, that's what it would look like completed, nice and clean. For those that do inspections on the Sherman-Minton Bridge out here, it all looked fairly similar. The end up results of this fix was very similar to what you'll see out of Sherman-Minton Bridge today. Aaron mentioned confidence, and this was a big important part of this, right? So if you have one crack and one major incident on this bridge, we have 500 other wells out here that may or may not have a problem, and we need to know what those are and what we're going to do about them. So while we were doing this inspection, HNTB was in charge of doing the NDT work, and they hired some people and went down through here to inspect the 500 other wells on the bridge that hadn't fractured yet, and trying to figure out what was the issues and how many of these had problems. They did have some. There was additional challenge that we ended up seeing there. What you see here, and this isn't the forensic part of it, but just to give you a kind of a precursor, this is the section that was taken out of it. And you'll see there that they have the weld region identified. In that same chunk of steel, there were 4 other surface breaking indications that would show up on an MT test. Again, all these on the inside, all these uninspectable in this particular bridge, but there was other cracks in this structure in the exact same weld that fractured. So that was kind of worrisome that we had, man, we need to try to look at this. And they had to recalibrate their NDT in order to anticipate and be able to identify these other small hydrogen cracking that they found in here. In the end, we ended up with multiple locations, a little bit challenging to see, multiple locations where we had to have large indications in the weld. For those, we would plate over the indications. For smaller indication, we would just go in there and take a core out, drill out that small indication and remove those from the bridge. So I think we had 17 plating locations in the end, and 15 or 20 places where we were doing the coring. Again, we continued to talk with the contractors. We refined our designs based off their input on what they said would be useful to some of these things. How can we go about the process to doing this easier and more efficiently? Here's a typical repair over a couple of these splices at the odd joints. The odd joints, as Aaron said, these are had additional, anywhere we had to have bolted to the floor beams, they had to upsize that very thin plate of the box girder. And at those locations, we had to, they had to have these full penetration butt welds. And again, if we had major indications, we would go in and do a plating operation. All the plates were designed such that if a fracture were to occur in that plate, these are catcher plates, they don't hold any of the dead load. It would only be in a case where a fracture event occurred, similar to what happened. Now all of a sudden we have something that can catch that load, can carry the load through, and not have the similar result we did before. Typical even plates showing up there. Several details. We ended up leaving a suite of all the different types of repair options, and so that we kind of have a pick and choose the menu as they found more issues with the NDT. Again, installing these things fairly similar to that. In the end, the bridge was closed for 83 days. You see the phase 2 plating in there. We finally opened it up after all the phase 3 plating or all the plating was done for the rest of the ties. Again, it was about a confidence for the public, ensuring them that the bridge was safe to open up and safe to traffic, and we're able to get that done. Talk about the forensic analysis on this. It's interesting to me what they were able to find, and I'm not a weld expert, but we pulled that section out of the bridge and laid it open and looked at it. You could tell there was a very, very poor quality weld in part of this. There was cracks, and the fracture surface looked rough, porosities, other issues were a problem with this weld. You'll see here that we have a yellow and a green area. I'll show another slide here in a minute of how this was. Those are considered the originating cracks. They believe these are hydrogen cracking. Essentially what happens when you weld something, you can get hydrogen embrittlement. Now, this was a problem when you had improper preheat and other issues. Today, we mitigate all those sorts of things on proper preheating, in addition to having inspection that occurs 48 to 72 hours after the weld. For this particular one, it welded, they probably did do a visual check, did not see an issue after the visual check, closed the box up, and it was never seen again. It did continue to expand, which we'll show here in a minute. One other area of note, at the area of the crack, there had been a previously identified issue here. So the picture on the right is what we see in a typical weld cross-section. This is a double beveled weld. So you kind of see the bevels coming in there, and how we have this relatively slim profile, right? All the little semicircles, those are weld passes. So this is a cross section of the plate. The top of the picture is the inside of the plate, the bottom is the outside of the plate, and you're looking at a section through the weld. That's what you're seeing there. And what you see with those little semicircles, those are the weld passes. When you do a thick plate weld, you have to have multiple weld passes over and over through to try to build up the weld material to get the weld completed, right? And so you're seeing that there. On the left side, it's a much wider weld, but what you'll also notice is that, I'll say the smiley face brother there, you can see that those weld passes were from the inside of this tie. So when this thing was originally built, there was some sort of defect found. They gouged out the defect and re-welded that whole thing and made a weld repair. After that weld repair was done, evidently, and this was happening, we had another hydrogen embrittlement crack in the repair. It actually in that repair that the weld and things happened. It was not the only one we found. We took some other cores out there from after the NDT. This is another core, and you can see here there are multiple cracks showing up on the inside of this box. Some of the welds that were had similar issues with hydrogen embrittlement. What ended up happening here, you kind of see this in the picture, we actually have multiple fracture events that occur. The yellow and green are the original fractures that occurred. There's kind of a light blue color in there. That was another fracture event that occurred at some point in the past. At that time, it combined essentially the cracks between the yellow and the green. But if you'll notice, there's still a little bit of the blue doesn't go all the way to the surface. That's the outside of the box. So at that time, there was a significant crack within this box girder, but it was not visible to the outside, and nobody could see it unless they had done NDT on it. At some point, there was this orange crack that went from about 3/4 of the height outside the girder and around on the bottom. Why that alleviated itself, why it did not continue to propagate, God only knows. But we do know from some evidence and some pictures that a kayaker sent that somewhere about 5 years before this, that crack was visible. When that happened before, we don't know. The fuchsia or purple pinkish color going across top, that was the last event. That event occurred within the last year. We can confirm that from other videos and evidence after the fact, but that occurred within the last year. That fracture event went up the top, came across the top of the tie, and the energy of that thing ran down the tie. There's a picture Aaron showed from the top where you saw that the top of the box had kind of unzipped. Fortunately, that weld of the top plate to the inside thing had a very poor weld. There's a lack of fusion there. So the energy of that crack, when it hits that, went to path of least resistance, which fortunately was down that crack and alleviated itself about 9 feet down the tie. If that had been a better weld and it had gone into the other plate, it may have unzipped the whole thing and would have fallen in the river. So that was a fortunate event, but what ended up happening on this project there. As we wrap this little talk up and try to explain the things, appreciate your attention on it. Some of the lessons learned, again, with anything, communication and collaboration. You have to be able to communicate, talking with the contractors, with the owners, with all the stakeholders involved, be able to communicate ideas, working towards a common goal. You're going to get there very quickly, especially when everybody's got a focus and motivation. I took a lot of internal, a lot of external meetings, right, that we're working through this thing. And we were able to use the CMGC process very efficiently, in my opinion. It did reduce the risk overall to the owner, to the contractor, to the engineer, as we kind of thought through ideas in a very collaborative way. We definitely improved constructability, right? Means and methods are important to the contractor, and we could get direct feedback from them. You know, would this be a better approach or that one? Material procurement, contractors are much better. We spent a lot of time in those first early weeks. I was talking to multiple, fabricators to find out, hey, what steel do you have available? How long of a plate can I design for you? And they were very open about this. This is something I would, talk to you. If you have issues like this or any time, call your fabricators. They're the ones with the material. They can get that sort of information. But the contractor was really much better at that. They were able to coordinate that stuff for us, getting bolt links, when could the lead time for those be. That was very helpful. But be prepared for challenges and setbacks. We're going down a lot of blind alleys. We're going to have a lot of dead ends that we run into. That's just part of the process and some of the fun, I guess. In the end, by the numbers, total repair cost was just under $10 million. The phase one steel was, 30,000 pounds. It's not a lot, but it was a lot really, really fast, right? Within 2 weeks, we had that design fabricated and out and installed on the site. Phase two was about 100,000 pounds coming through there, 4,000 bolts, and about 1,400 feet of PT rods. For phase three, I think one of the things here, we had 1,200 feet of welds. The NDT testing had multiple inspectors. That was a 5 or 6 week operation to try to get all that stuff done. So it was a major operation by a lot of key stakeholders in order to make this happen. With that, I think that gives us just a few minutes here to answer any questions you might have, and appreciate your time here today. Thank you.
Are they gonna increase the inspection frequency on this bridge?
Going forward?
Yeah.
I believe at this point they're going to still keep it on the biannual. I think that Arkansas is currently reviewing their entire program. That was a part of this coming out there. FHWA went in and did a full review of their inspection, load rating, and kind of their entire program of QC and all that stuff. They've since hired a consultant to go through as well to do a review, and they're going to go through a full review of the process, looking at each of their procedures, providing a questionnaire of what's happening with that, and trying to benchmark them to other states within the country and try to provide suggestions to improve that. So, yeah. Yes, sir.
So Arkansas is responsible for the inspection, but Tennessee is the lead on contracts. Is that right?
Yeah, so it's an interesting situation. So in Kentucky here, when we have the cross river bridges, we have, Kentucky inspects and maintains and kind of the lead agency for about half the bridges, and they alternate with the adjacent states, Illinois, Ohio, Indiana, etc. But for this particular bridge, and I don't know why that is, but Arkansas is in charge of inspection for the project, which was a little bit unique for it. I mean, so Arkansas inspects all of their bridges with in-house staff. They don't have consultant inspectors for their bridges. The only bridge that they do with consultants is this bridge, and they don't even do all this bridge. Michael Baker was just called in to do everything above the deck, the arch rib. It's too tall for them to get manless in there, and they don't have the rope access personnel. And so they had hired us just to do that portion of it above the deck. But yes, Tennessee is the one that actually is in charge of the contracting and doing any repairs that goes through Tennessee. They share costs for all the aspects, but they manage it in a slightly different way. That's correct. Any other questions? I don't know if you're the only one.
I have a question. Can you talk a little bit about how you looked at early on in the bridge, you were talking about assessing sort of how much stress it was having. So how did you assess what type of equipment you could get on the bridge during construction?
Yeah, so how do we assess the amount of equipment we have during construction? So what we ended up doing on this particular project is we started off with very basic analysis. Aaron kind of showed us, let's look at P over A, right? And then we just kind of take each step from there. And you say, well, if we can, we know we have a little bit stronger material, but then we don't know what the well on the other side is. It actually in good shape. We don't have any tests of the other. Maybe the other well has a big crack in it. We don't know, right? So it kind of is that. Well, now we do think it's getting warmer. So as it warms up, these have some friction pendulum bearings. Then they ought to be adding a little more compression to it as this whole bridge warms up. It was May when this happened. We're getting into summer. That's a good thing. But then the thought process comes through your head. Hey, well, what if, these friction pendulum bearings break loose? If they sit still until they break loose with the friction, and then they'll move. But what if they're holding compression and then the temperature swing comes off and it breaks loose? Well, that's even worse. So this is one of those projects, about every time we had a good thing to think about, we had another opposite thing that was a challenge and it worried us. And you sit up at night going, man, what are we're gonna wake up the bridge in the water tomorrow. In the end, we said we knew this bridge had been carrying traffic for 6 months to a year time frame. We knew there was a certain amount of vehicles running over. We get to see videos of trucks running on the bridge. So there is something here holding this bridge up, and it hasn't fallen down 2 days. So if we remove the traffic, we can say we're going to have a truck that's run over this. We know there's probably been some fully loaded truck, probably more. So we kind of use that as our base to say, this is something we know has happened. If we feel that that's comfortable with it, then we're going to say, contractor, you can use up to this amount of load, of what would be a truck in the worst part of this bridge. So as you go in here and install, we call it the dance floor, this big platform, right? That platform is going to take, 2 KSI of stress. If the truck was 5, that means you can add 3 other KSI worth of live load on this side of the structure. It's continuous structure, huge span continuous. So when they come up from the Arkansas side, this was on the Tennessee side of the 2 spans. We basically said, if you come up on this side, you're not adding stress to this particular tie. So all material needs to be come in from the Arkansas side to get up there. And so that's where we kept most of the load. And then Aaron showed a picture with the chain falls all through there. They would pick it up off the trucks at the pier and then swing it down through there, the heavier loads, until we had it stabilized and had post tensioning in place. So that was an inexact science is the right answer, because there's no correct answer to this. It's just, how comfortable do you feel with it, with being uncomfortable? Any other questions?
All right, thanks.
All right, thank you.